All right, so the reflexive property, what it said is that a segment is congruent to itself, or an angle is congruent to itself. And we use that when we needed it in a proof to show similarity or congruence. So we might have to say that segment BC is congruent to segment CB. They're the same thing. So it's congruent to itself. So that may have been one of the statements in our proof. And if this was the statement, then our reason was reflexive property. Do you guys remember that? Yes. Okay. Some of the other properties that we could use are properties of equality. So we have addition, subtraction, multiplication, and division. And what that states is that if we have two quantities that are equal to each other, if we add equal amounts to both sides, it's still equal. If we subtract equal amounts from both sides, it's still equal. If we multiply both sides by the same amount, it's still equal. If we divide both sides by the same amount, it's still equal, as long as that what we're dividing by is not 0. So that's the addition property of equality, the subtraction property of equality, the multiplication property of equality, and the division property of equality. So those were some of the big ones from that section. It also talks about the substitution property. So if we have two quantities that were equal, we could take one and plug it in for the other. That's all the substitution property tells us. We also looked at the transitive property. We didn't use that one as much. It says if, let me write that down. Transitive we did not use as much, but here we go. Transitive property would be if A equals B and B equals C, then A equals C. That's the transitive property. I think we use that in one or two proofs, but not as regularly as we did other things. You see reflexive property a good bit. You may see some of these. Substitution property we used. Transitive occasionally. All right. Does that refresh us on those? Those of you that are writing, I'll give you just a minute more. Okay. Then we moved on to if we have two parallel lines cut by transversal. So if we look at our picture, we have lines M and N that are parallel. How do we know? Because they're marked with the arrows, right? The arrows tell us parallel. So we have parallel lines M and N cut by transversal L. Lots of things are congruent. Angle 2 is congruent to angle 6, which is congruent to angle 3, which is congruent to angle 7. All of those are congruent to each other, aren't they? And then 1 and 8 and 4 and 5 are all congruent to each other. And let's talk about why. We know that angles 2 and 3 are congruent. Angle 2 and angle 3 are congruent because they are vertical angles. And we had to use that in proofs, didn't we? Vertical angles are congruent. We know that angles 2 and 6 are congruent. Angles 2 and 6 are in the same position. They're both the top right above their parallel line. So those are called corresponding angles. We know that corresponding angles are congruent. Angles 3 and 6 are congruent. If we look, they're on opposite sides of the transversal. Those are called alternate interior angles. And alternate interior angles are congruent. 2 and 7 are congruent. They are alternate exterior. So we can prove these congruent because we're given two parallel lines, and we know that all of these things must be true. Now the last thing is the same side interior angles. So if we look at 4 and 6, they're on the same side of the transversal inside the parallel lines. So same side interior angles are supplementary. And what does supplementary mean? Adds up to 180. Okay, now this stuff is really an 8th grade topic. Do y'all remember it? It's actually in regular 8th grade. So y'all may have seen it in 7th grade, actually. But we had to use all of these things in our proofs. Do you have any questions about those big ideas? Okay, so they could give us a lot of problems. Like they might give us the measure of angle 8 is x plus 5, and the measure of angle 4 is 7x minus 11. Find x. And then we just set them equal to each other and solve, right? So they could present us questions. What I think they'll do is put something like this inside of another problem, where you have to know this to be able to work a different type of problem. Okay, now perpendicular lines. We know that perpendicular lines form right angles, and the definition of a right angle is it's an angle with a measure of 90 degrees. Now, if we have two lines that are perpendicular to the same line, then those two lines must be parallel. So we know that the upside down T means perpendicular. It indicates a right angle. The measure of a right angle is 90 degrees. So if we have two lines perpendicular to the same line, then those two lines must be parallel. Okay, so this review that I'm doing today follows along with your book. So if you're using your book to help you study, or you're using your workbook, or can't really use your book because we have to turn those in, the online textbook, it follows along in the same order. So the next thing the book went to was congruence transformations. And this is where we're trying to prove that two figures are congruent. And to prove that two figures are congruent, we can use three of the transformations we studied. There are rigid transformations. And our rigid transformations are translations, rotations, and reflections. Because those three don't change the size or the shape of the figure. So those three we can use to prove congruent figures. So here's an example of a translation. This is my pre-image. It's a flag right here, and this end point of that segment is 3-1. This one is congruent. We'll pretend it doesn't really look it, but we'll pretend it's congruent, and it's our image. And that same end point of the flag is at the point 2, -2. So to prove translations, you're just showing that you're adding something to your x and you're adding something to your y. So what can I do to shift from the pre-image to the image? We could write it as a mapping. xy goes to x plus 5 and y minus 3. We have used a mapping to prove congruent figures. Do you remember that? Good. All right. Maybe next week, every day, we should have an extra cup of coffee. Y'all look a little worn out. I can see you all going home, telling your parents I asked you to drink coffee. Or at least get enough sleep that you come energized. All right, the next one, reflection. So we can prove congruence using reflections. The main reflections we did were reflections over the x-axis and reflections over the y-axis. If we reflected over the x-axis, we reflected over the x, what changes? The y. So xy goes to x negative y. If we reflected over the y-axis, the x changes to the opposite. Okay, the last transformation that yields congruent figures is a rotation. And what we studied were rotations about the origin. So if you're trying to write the mapping and it's not rotated around the origin, the first thing you have to do is shift it back to the origin. Then do your rotation, and then shift it back to the new center of rotation. So the center of rotation has to be shifted back to the origin, rotated, and then back to the center of rotation. rotations. It should be denoted as counterclockwise, because when I give you a positive rotation in mathematics, that should be counterclockwise from the x-axis. It should look like this from you. So we're talking 90 degrees like this. Okay? Now, I'm not certain how they're going to word it on the end of course test, because we teach it just the way you're going to do in upper level mathematics. If it's positive, it should say counter, it won't say it. If it doesn't specify anything, you're to assume counterclockwise, because in mathematics, that's what it should be. But I don't know who wrote it or how they wrote the end of course test. So when we think about this, if we think about a 90-degree counter, you see that's the same as a 270 clockwise. So you just may have to think about these. I'm just not certain what form they're going to give it to you. But a 90 switches the x and y and changes the y to the opposite. A 180 just changes them both to the opposite. And a 270 switches the x and y and changes the x to the opposite. You guys have a lot to study to prepare for this end of course test. I would try to learn these, but if you get to the test and you get confused, draw a quick sketch, see if that helps you figure it out, you know? See if a 90 degree, you can figure it out that way. If you can't, pick your favorite letter of the day. I'll make mine B. I'm going to fill in B if I can't figure it out. I'm going to put a big star in my book that says the star to me means I totally guessed on the answer sheet. If I have time at the end, I'm coming back to this one. No. So if for some reason your brain fails you on something, and let's say rotations is what it is. You remember, I'm supposed to switch something and change some sign, but I can't remember what. So if you don't remember, choose an answer, put a big star beside it in the book, and if you have time at the end, come back to that problem.
When
yes, sir?
Switching the y and the x, like if you had the point 2, 1, would that be like negative 1, 2?
Yep. And
then so on your graph, the negative 1 would be the x coordinate then?
Yep. Exactly. A 90-degree rotation would put this at negative 1, 2.
Okay.
So if I called this 2, 1, then this would be at negative 1, 2, 90 degrees. Okay. Any questions about translations, reflections, rotations? All right. Okay. Similar figures. Now, when we do similar figures, that's going to be our dilation. That's a non-rigid transformation. So the pre-image and the image don't look like the same shape. Excuse me. Same shape, different size. They are the same shape, different size. Okay, so here we'll consider the small one, our pre-image, the large one, our image. How would you find the center of dilation? Well, one way is to draw lines through corresponding points. So I drew a line through these two corresponding points and these two corresponding points for the pre-image and the image. And the intersection right here is the center of dilation. And I think you had one of those on your practice problems, didn't you? Yeah. Okay. This appears to be a dilation by a scale factor of 2 through the point, negative 2, 0. When we look at dilations, what we're doing is we're multiplying both the x and y by a constant, and the constant has to be greater than 0. If it's less than 0, then that also indicates a rotation of 180. It makes them both negative, right? Or a double reflection of the x and y. All right. questions about this? If you had to write a mapping for this, a dilation that was not at the origin, the first thing you have to do is shift the center of dilation to the origin. And then multiply by the scale factor. And then shift back to center of dilation. You guys remember that? So if I were to write a rule for this one, it would say x, y goes to, well, I got to shift it over to the center, so it would be 2x plus 2, y, because I don't have to add anything to my y. And then I'd have to multiply through by 2, so it'd be 2x plus 4, y plus 2. And then I'd have to shift it back, so it would be 2x. To go back, I'd have to do minus 2, so it makes it 2 there. And that's what it would look like. Let's see if that would work. This point is the point 1, 1. So if I plugged in 1, what do I get out? 4. If I plug in 1, what do I get out? 3.
Wait, shouldn't it be
It's just
2y
2y, not 2y plus 2.
Thank you. So I get out 2. And that's the right point now. Thank you. Okay. Triangles. Yes, lots and lots of triangles. Okay, so the first concept we looked at with triangles is that the sum of the measures of the angles, A plus B plus C, the sum of the measures of the angles always equals 180 degrees. And then the second thing we looked at with triangles is if the sum of the two remote interior is equal to the exterior. So the sum of A plus B equals the measure of D. Do y'all remember that? No. You can figure it out the other way, yes.
I don't think
I don't know if we went in depth with that, but
It was real quick. It was approved one day, and we used it
makes
on
sense.
one set of homework. That's what we did. So you might see this one something like this. Let's say this is 120, and this is 2x, and this is x plus 5. Find x. So we'd say 2x plus x plus 5 equals 120. So 3x equals 115. So x equals 3, 5, 35.
it's 105.
Yeah.
Yeah.
105.
35.
35 times 3 is 105.
I didn't do that right. 30. Ooh, it's ugly.
Yeah.
Take
Yeah.
37.
That's what 115 over 3.
So it leaves me 25, so that would be 8 and a third. That's ugly.
Sure.
There we go. That's better. Okay. All right. Then we looked at all things triangle congruent. So to have congruent triangles, also congruent. So what postulates and theorems did we use to prove congruent triangles? There were 5 of them. Okay, side, side, side.
Angle,
3
angle.
sides of one triangle are congruent to 3 sides of another. Side, angle, side. A side, the included angle, and a side of one triangle is congruent to a side, the included angle, and a side of another triangle. Angle, side, angle. An angle, the included side, and another angle is congruent to an angle, the included side, and another angle of another triangle. Angle, angle, side. That's where we have 2 consecutive angles and attached side are congruent to 2 consecutive angles and an attached side. And then HL. The big deal is you have to start off with a right triangle. Otherwise you don't have an hypotenuse, right? So we have a right triangle with a hypotenuse and a leg congruent to a right triangle, hypotenuse, and leg. What is the one that does not work?
Donkey.
Yes, we called it the donkey. It's this one. That is not a congruence postulate. You cannot use it. If they put it on there, they'll put it like this. This is not a congruence postulate, so don't let it trick you. Okay? Now, once you have proven congruent triangles, once you have proven they are congruent, then you can use this to prove that other things are congruent about those triangles. And CPCTC, what does that mean? That corresponding parts of congruent triangles are congruent. So we use that after we used one of these 5 to prove congruence.
Wait, so when is that used, the last one?
This,
After.
okay, if we prove that something's congruent by side, angle, side, and we want to show that the base of one triangle is congruent to the base of another, and it wasn't something we used in the proof, then that might be our last step. Show that AB is congruent to DF. And we would know that because we just proved congruent triangles, therefore corresponding parts of congruent triangles are congruent. Okay. Isosceles triangles. What do we know about isosceles triangles? They have 2 congruent legs, and their base angles are congruent. What's the name of the other angle? The vertex angle. So, how would you see this type of problem? I don't really know, but I know how I've seen it on the SAT. And so, let's say I told you we had an isosceles triangle, and the ratio of the vertex angle to the base angle was 1 to 4. Find the angles. Or find the vertex angle. So since we know it's 1 to 4, when we're not certain of a value in math, what do we use? A variable, x. So it's 1 times x to 4 times x and 4 times x. So how many x's are there? 9. We know their sum must be 180, so x is 20 degrees. Okay, equilateral is also equiangular. So if we have 3 congruent sides and we also have 3 congruent angles, and each angle has a measure of 60, and this was great because what did we do with those all the time? We dropped down a perpendicular and turned them into 30, 60, 90 right triangles, and we'll talk about right triangle trig next week. We good? All right. Our favorite, triangle centers.
Oh, God.
Also known as points of concurrency. Okay, so breaks we got because of the snow days. I Googled mnemonics for triangle centers and points of concurrency until I finally found one that I thought I could remember. And it's this one. All of my children are bringing in peanut butter cookies. So all of, altitude, orthocenter. So if I drop down a perpendicular, that's the altitude. The intersection of two altitudes gives me the orthocenter. My children, medians. A median goes from a vertice to the midpoint of the opposite side. The intersection of two medians gives me the centroid. Are bringing in angle bisectors gives me the end center. The end center is the center of a circle that is inscribed inside of a triangle. Peanut butter cookies. Perpendicular bisector circumcenter. So if we did the perpendicular bisector of two sides, that intersection is the circumcenter. And I can circumscribe a circle if I put the point of the compass at the circumcenter and then put the pencil part on one of the vertices and circle it around. Okay, so if you see one of these, I really think it's either going to be the end center or the circumcenter because they were twice last year.
So how much compass straight edge work are we gonna have to do?
I think you'll just have to realize what it is and not actually do it because the whole thing is multiple choice, right?
Mm-hmm.
So you will have to understand markings, maybe.
Okay.
I think that's more what it'll look like. I just can't make this stuff go away. Alright, so in center, I'm just going to hand draw it because actually doing it with the other thing is really hard. So if I started with the angle bisectors, so to do an angle bisector, the point of the compass goes here, we arc, and then switch it, and we arc, and then that gives me an angle bisector. I bisect another angle, arc, and then switch it, and arc, and that gives me an, whoops, I'm way off. There we go. So this point right there is the end center. And then if I do the perpendicular to a side, and the way I do a perpendicular is I'm going to switch to a different color, perpendicular to a side. From here, I would arc here and here, equidistant, not moving it, here, and then shift here and here, and then that would give me the perpendicular to a side so that I can use that, measure from here to here to draw in, oh, that's terrible. It should be touching in one point right here, right there, an inscribed circle. Okay, if you have forgotten how to do this, my links on the website are still there from last year. So if you go to my website, and these are circles, in center and circumcenter. So unit 10 is circles. See how they're labeled? Circumcenter. This is how you do it. Perpendicular bisector. This is slow. Perpendicular bisector. Remember with a circumcenter, it doesn't have to be inside the triangle. It'll be outside if your triangle is obtuse. On it if the triangle is right. And there we go. Circumcenter gave you a circumscribed circle about the triangle. And then you could do in center and oh, it's too slow. I don't have time. But you can. You can later on. It's slow. Alright. So those are there we go. Incenter is equidistant to the side. Circumcenter is equidistant to the vertices. Centroid puts it into a 1-to-2 ratio. Any of that sound familiar?
Nope.
It's just, okay. Yeah. Centers are hard to remember. Okay, then we did mid-segment. Do you guys remember mid-segment?
Partially.
Okay, good. Just kind of makes sense. If we go to the median of one side, the median the other, perpendicular, not parallel to the base, then this DE is 1/2 the BC. Alright, looks like we only have 3 more slides. Woohoo! Oh, this is a biggie there. Proving quadrilaterals. Okay? So our quadrilaterals, we had the parallelogram family. In the parallelogram family, it started off with parallelogram. By definition, a parallelogram is quadrilateral with 2 pairs of parallel sides. Okay, that's the definition. So we can use that to prove. Now, if we know that opposite sides are congruent, we can also prove we have a parallelogram. Opposite angles congruent, then we have a parallelogram. If we have one pair of sides that is both congruent and parallel, the diagonals will bisect each other. And if we have one angle that is supplementary to both of its consecutive angles on either side, it has to be supplementary to both, then we have a parallelogram. Okay, so those were the ways we showed a parallelogram. Rectangle. It has to satisfy one of these and show that it either has a right angle or the diagonals are congruent. Not only that they bisect each other, but they are also congruent. Okay, so that would prove a rectangle. To prove a rhombus, one of these plus show that 2 consecutive sides are congruent. We know in a rhombus that really 4 are. All 4 sides are congruent. But we only have to show, if we show one of these, then we only have to show that 2 of them are. The diagonals are perpendicular, and that the diagonals bisect the pairs of opposite angles. Now a square. A square has to have 1 from the rhombus, 1 from the rectangle, and 1 from the parallelogram. So we have to prove parallelogram, rectangle, and rhombus to make it a square. Did y'all learn all that last year? Not really?
You just made us figure it out.
Okay. Well, those are the rules, all summarized on one page. Yeah, you certainly can print that page. Because I will save the notes as a PDF, and you can just print out whatever you need. Okay, that's too much for you to copy, so y'all can print that one. All right. We've already talked about congruence. We mentioned similarity with a dilation. If we have a transformation involving a dilation, the result is a similar figure. We already talked about this. You have to shift the pre-image to the origin, then dilate, and shift back to the image. Okay, let's do scale factor of 3 this period because, well...
Why do you have to shift it back to the origin before you dilate
because what you're doing is you're multiplying those numbers, and all you really want to do is double the distance. And if we don't shift it back to the origin, then we're, instead of just doubling, it has to be at the origin or we're making it more than what it says. Okay, so the mapping for this one, if this is our figure, first we'd shift it back to the origin, so this point would have to go left 2 and down 1, and then we multiply through this class period, we're going to do a scale factor of 3, so that would make 3x minus 6, 3y minus 3, and then we're going to shift back to this point. So we're going back to 2, 1, so we'd have to add 2 and add 1. So the mapping would look like this. It would be 3x minus 4 and 3y minus 2. Okay? Not sure if they're going to give you mappings like this, but we did do them. So, y'all didn't do a whole lot of mappings?
We didn't do it, but they didn't tell us to shift back to
Okay. Okay.
Just did it from our
Did it wrong.
we fed for ourselves.
Well, some books just say it in words. You would have to dilate by a scale factor of this, and they might say through the 0.21. And if we said through the 0.21, we wouldn't have to talk about shifting. You may have done it that way. But if we don't define it, it's through the origin. All right, so similar triangles. Now we're to similarity. We have 3 theorems and postulates we can use for triangle similarity. Angle, angle. If we can show that 2 angles of one triangle are congruent to 2 angles of another triangle, we have proven similarity. Side, 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 and side, angle, side. But this time, side, 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 instead of showing congruent, we are showing that they are in the same proportion. So if we have 3 sides of one triangle that are proportional to 3 sides of another, the triangles are similar. We can also use side, angle, side. So we're going to have 2 sides that are in proportion, and that included angle would be congruent. So we'd have to have those to do similar triangles. So instead of congruent, we're throwing in the word proportion. Now, angle, angle only works for similarity. Does not work for congruence at all. Oh, that's it. We did it.
We did it.
Okay, so let's go back and look what I added to our website. Did we talk about this yesterday? It's 2 60-minute tests, 31 questions each. This is the breakup of the problems. Okay,
That's over 2 hours.
so here are some of the problems. I really think I should have put my Unit 7 in here too.
Oh, okay.
I just
I'll go back and look at
last time slowly.
What now?
Yesterday I was thinking that meant that we had to do 2 questions per minute, but it's actually 2 minutes per question.